so this talk is kind of going to be a mixture of things. So I'll be presenting a couple of parts, and then Phil will finish off and present some other stuff. So the work's all along sort of a similar line, so please feel free to interrupt if you don't understand anything, so that then you understand sort of the stuff towards the end of the talks and get a better idea of what's going on. Okay, so in general, what we're going to be talking about today is the idea of inducing grammars from text. So we all know that language is hierarchical, that it's recursive, so therefore we want to naturally model it as a tree. The big challenge is, can we actually infer or induce decent trees directly from text without access to linguistic resources? And if we look at the kind of things that we've seen in the literature, we have sort of some short sentences like the example here. Perhaps we know the part of speech tags. And then the state of the art here, annotated, is coming up with a tree that looks like this. Obviously, it's pretty impoverished, as we can see, but it's perhaps learnt to group together some noun phrases into a unit, grouping together a verb phrase unit, and sort of learnt the constituency structure, but it hasn't really learnt much more. And while that's state of the art, what we'd really like to learn perhaps is something a little bit more advanced, or perhaps we might want to go a lot further and start annotating for a whole lot of other things, like what you've been doing here for many years with your tetragrammatic representation. So sadly, of course, state of the art, we only have the pos, or assumes that we have the pos tags, and can infer some sort of vaguely plausible trees with, say, 60 or 70% accuracy at the very best. Once we throw away the pos tags, we're kind of in an uncharted territory. Once we start looking at sentences of length 30 or 40, it's complete and utter abysmal failure. So in general, I think this is kind of one of the really interesting ways of pushing natural language processing and trying to actually learn from data, but we're a long way from getting anywhere useful, purely in an unsupervised setting. But it shouldn't stop us from trying, because so here's a potential interesting application. So one of the sort of end-user applications of NLP, machine translation. So we've got a sentence, say, in English. We've got the same sentence in Chinese, and what we want to learn is to, say, translate English into Chinese or Chinese into English from this kind of corpus. And if we were to know the syntax, then that can really help us to do the translation. So if we know that every corner of Singapore is a noun phrase with a prepositional phrase modifier, then we know that this is pretty common, that we're going to see, for instance, the preposition becoming a postposition in the Chinese. We might see a reordering among the noun phrase itself. And this can kind of drive both our lexical selection of how to translate these units and how to actually order them to form a coherent sentence. So what we're kind of interested in is if we can do some kind of grammar induction to learn these translation models. This is the overarching aim. And these kind of, perhaps our grammar induction learns something like this, something pretty impoverished, but can still kind of help us. So we learn perhaps that these kind of things in blocks are units of translation, and perhaps we learn that there's some kind of reordering going on here, some reordering going on here, there's some monotone translations going on here. So we know how to glue together the units to get from one language to the other. And this is kind of maybe what you might see as state-of-the-art in grammar induction in bilingual, from bilingual data. And it's kind of relatively understudied. And Phil will be talking more along those lines later on. What we'd really like to see is something a little bit more linguistically motivated. So we'd like to see that it learns that sort of there are things like noun phrases. There are maybe things with interesting categories like CCG categories, a verb phrase missing a noun phrase to the right, and other kind of types of categories. And also things like license reordering being quite important for translation. So sort of this is the overarching aim. Can we learn some kind of induce some kind of interesting grammar from bilingual corpora that is going to inform our translation both in lexical selection and in gluing together and creating coherent strings in the right order. So now, in this talk, I'm going to start with what I call somewhat supervised grammar induction. So I start with a monolingual setting, then I move to a bilingual setting, and Phil's going to finish off with more stuff in the bilingual setting. So to start with, we're talking about tree-substitution grammar parsing. So it's also known as data-oriented parsing in the literature. And the idea is that we're trying to learn one of these grammars, a reasonably rich grammar representation, that can learn very large units from a tree bank data and can use that to parse efficiently. And good accuracy. And in the second part, I'll be talking about applying this kind of model, but to bilingual data. So where we're given a parallel text, half of it's parsed and the other half isn't. So one language is parsed, the other language isn't. And we're trying to learn a string-to-tree transducer. So it can take strings and create trees. And this is a similar model, except it's bilingual, so everything gets a bit more complicated. It also has an alignment problem, and you have to know which words translate to which words. And we can learn a grammar again of tree fragments and tree string pairs and substring pairs. And in the last bit, which Phil will be presenting, it'll be sort of removing the reliance on any syntax whatsoever and trying to do this completely unsupervised in the bilingual setting. So it's inducing a grammar from scratch. Okay, so the outline of the talk. First, the parsing section. Second, we'll talk about machine translation with a synchronous tree-substitution grammar. And finally, I'll conclude. So I'll just start with the parsing. So syntax is obviously a core discipline in linguistics. And what people have traditionally tried to do is distinguish between what's grammatical and what's agrammatical. However, we're sort of firmly within the statistical camp, and we'd like to grade utterances with a score. Are they reasonably well-formed? Are they very well-formed? Or are they complete rubbish? And we'd like to get something in between. We believe, well, this is sort of quite a lot of parsing has gone down this avenue in the last 10 or 15 years, and we're looking to sort of continue along that line. We seek to learn the model's parameters from tree bank data, so we're given some linguistic input. And then we seek to predict a parse structure on unseen test sentences. So obviously this is an invaluable pre-processing step in many, many tasks. Now, in statistical parsing, the simplest models are still winning the race, I think it's safe to say. Of course, you can argue about evaluation metrics and so forth, but in general, context-free grammars are sort of underlying all of the powerful and well-known models. And it's kind of interesting, because if you apply a context-free grammar from scratch to the tree bank, you get abysmal performance. It's really, really bad. And you have to go to reasonable lengths to actually get it to perform well. And in general, the way people do that is by injecting linguistic information into the representation. So instead of talking about noun phrases, you perhaps talk about a noun phrase headed by a certain word, like cat and so forth. So to get state-of-the-art performance, you have to do a lot of injection of dependencies, clever smoothing, a whole lot of other transforms using linguistic knowledge of the language. But, and that is what we're looking at in this talk, can we get there without actually specifying this knowledge? Can we learn it from the data? Is it actually inherent in the tree bank such that we can actually infer it? And there are a few ways which we might go about inferring it, and people have tried sort of various different approaches. So one is to infer a richer set of non-terminals. So, for instance, instead of talking about noun phrases, we cluster the noun phrases. So there are certain types of noun phrases, and this, for instance, we have noun phrase type 3, perhaps we have plural noun type 5, and so perhaps some kind of nouns are the ones that tend to take female gender, other types of nouns take male gender, some of them are days of the week, and so forth. And this can learn sort of more interesting dependencies and sort of weaken a lot of the context-free assumptions that are made by a context-free grammar by allowing a lot more information to be injected into the non-terminals. Other ways that you can do it is perhaps to infer good lexicalization patterns so that you know, without telling it beforehand how to get the head, you can actually infer the head, and there's been some work in that regard as well. And the way we're going to look at here is inferring deeper rules. So rather than having all these very shallow rules, we're going to talk about rules that have deeper structure and perhaps some lexicalization in them. There are potentially a lot of other ways to do this as well. I think it's an interesting research area. Okay, so there's one kind of problem in that you can never expect to see every possible event in your training sample. So smoothing is absolutely critical to these models. And the larger the training set, the more data we have, the more parameters we want in our model, and we want to smooth less. So if we've seen a massive million tree training set, then we probably don't have to smooth very much at all. If we've only seen a few thousand, then we're going to have to smooth a lot. So a lot of the models in the literature don't really take this into account. They're very much designed for the data set that they're being trained on. And this is where non-parametrics come in. And this is kind of our motivation for using a Bayesian non-parametric model. So these models do not fix the number of parameters a priori. Instead, the idea is that they can grow with the amount of training data. You throw them a small training set, they'll learn to rely on their prior. You throw them a large training set, and that will overwhelm the prior, and they'll start sort of representing the data more explicitly with more parameters. And so typically this is following some kind of power law. So the number of training samples that you need to justify a larger grammar grows and grows and grows and grows. It's quite an elegant way of doing it, of reducing the capacity of the model, and reduce the model complexity, reduce overfitting. And in general, these are applicable to many NLP models, and you see in the literature that there's lots of people jumping on the non-parametric bandwagon and developing new models for lots of tasks. In some ways, they're quite applicable, and you can judge for yourself, perhaps, for some others. Okay, now I've forgotten how to use this. Oh no, here it is. Okay. So, wait a second. That's better. Sorry. Okay, so the next section, I'm going to talk about tree substitution grammar to give you a bit of background, and then I'll get around to sort of describing the model and so forth. So, the basis of most parsing is some kind of context-free grammar. The idea is that we have non-terminals and terminals. The productions in our grammar rewrite a non-terminal as some list of terminals and non-terminals. And our generative process, we can describe it in a probabilistic way. We start with the start symbol. We rewrite it as some number of symbols. We rewrite all the non-terminals in that string with more symbols. And we keep going until we only have terminals left. And our sentence is then created by reading off the leaves, which are all the non-terminals in order. A tree substitution grammar does something similar, except in each case it rewrites non-terminals with elementary trees, so they're larger fragments. And these trees can be any tree structure. They can have a mix of terminals and non-terminals as their yield. So if you read off all the leaves of these elementary trees, you can have non-terminals and you can have terminals. So in fact, they're a special case of a context-free grammar is a special case of a tree substitution grammar. The generative process is essentially the same. You rewrite a symbol as using a production, and then you rewrite the non-terminals that are remaining in the frontier of your tree that you're creating. And the reason why we do that is that these large elementary trees can describe very interesting phenomena that we see in syntax. So for instance, agreement, subcategorization, idioms, all these kinds of things we can represent quite succinctly in single tree fragments. So in general, this is similar in name to things like grammar engineering, where we start trying to adapt the non-terminal set in the CFG. It's similar to state splitting and other kind of methods for making your CFG a little bit more powerful. And in fact, you can actually do a reduction of tree substitution grammar into a context-free grammar that has a similar effect. Okay, so just to give you an example. So here's a very toy example. We have the sentence, George hates broccoli. And I've shown here two different tree substitution grammar analyses for it. So on the left here, we have one large fragment, which has the verb hates in it, and two NPs, and then we have the two NPs for George and broccoli. And these are shown here in just bracketed notation. So the top one being S rewrites as an NP, and then a verb phrase fragment with hates and an NP. So it's on the frontier, we have two NPs. In the second tree, we have a different derivation for the same sentence. So this is one issue with this kind of model, that we do have this derivational ambiguity. And in this case, we've chosen to do a different splitting, and we choose to have a substitution site at this V denoted by the arrow. So we get a much larger fragment for George and broccoli, and we get one for hates. So you could kind of argue in this instance that both of these trees have some plausibility. Both of these derivations are somewhat plausible. This one describes the frame for hates, saying that it's a transitive verb. And this second one denotes that there's some link between George, perhaps a semantic link rather than a syntactic link. There's some link between George and broccoli. So tree substitution grammars, just to sort of summarize, they're a generalization of CFGs. They're in fact weakly equivalent to CFGs in that we can reduce from a tree substitution grammar into a CFG, and it can describe the same string language. When we start injecting probabilities into it, then we can actually describe some more interesting syntactic phenomena at the tree level, and that's why it's interesting to us. The challenges that we get by embracing this formalism is that we get this derivational ambiguity. Multiple different derivations lead to the same tree. And we get this this problem at training time. So how do we obtain these trees? How do we define our grammar? And how do we weight them? And it's not completely obvious. Whereas CFGs, all the maths works out very nicely and they're very, very simple to estimate. In the case here, the maths isn't quite so nice. And that's kind of what I'm going to be talking about. So previous work in TSGs come under the banner of data-oriented parsing. Also, there's tree-adjoining grammars, which are a sort of superset of tree-substitution grammars. They have an extra operator which allows them to describe some slightly more interesting phenomena, but they also contain the substitution operator and can have arbitrary large trees. And there's also some work on adaptive grammars, which are a special framework for learning unsupervised deep trees from data. And effectively what we've done in this work is taken the adaptive grammar framework and extended it such that it can support full tree substitution grammar. And we've done it in a similar way to the adaptive grammar paper of Johnson. So just to compare with DOP, which is the main body of literature on tree substitution grammar, it has a stated aim of using all subtrees in the training data. So you give us a training set, we're going to cut it up the exponential number of ways that we can, and we're going to get statistics from all of the trees and use them then in order to parse. There are an exponential number of these subtrees, so this is kind of a problem for DOP, and there are various ways of addressing that. And there are sort of almost more numbers of estimators than I could fit on a slide, so I've kind of just put the predominant ones here. They had a sort of heuristic estimate that was kind of improved after some problems were shown with it, using a maximum likelihood estimate, using expectation maximization. There were certain problems with that as well. It has a degenerate solution where it does nothing. It learns entire big trees. So there have been sort of some recent work in trying to properly regularize the model. One way using this held-out estimator, another way using some kind of explicit heuristic process to regularize the model. So in general, there's been some good empirical results with this framework, but there are theoretical problems with quite a few of the estimators, and there's no sort of clean, clear, simple probabilistic model, and that's what the work here is doing. So it's a Bayesian alternative to the DOP estimators, and it's set up as a very clean and simple model. And the idea is what we're doing is we're talking about a generative model of an infinite grammar. So each non-terminal can rewrite as any possible subtree that starts with a given symbol and creates any type of tree of any possible depth. So if you were to generate from this, you could feasibly get an infinitely large tree. And what we do at training time and the way we set up our model is, because it's infinite, we need to bias it so that we can work under it in a finite sense. So we bias it towards being small. So we try and seek to find as simple as possible grammar. And we still want to also model the data. And the way we get this simplicity into our model is using a prior. So the prior is set up explicitly to bias towards sparse non-terminal expansions. So we don't want any non-terminal to rewrite as thousands of different productions. We want them to write as very few. We want most of the probability mass to be put on very few rules. We also want each individual rule to be small. So we don't want any rules that are of depth 10 or something silly, because they're not going to generalize to new data. And then the way we learn this is using an unsupervised induction technique. So we're given tree-banked input, and then we try and induce, given this prior and this framework, the types of segmentations and the types of grammars that fit our bias that we want here. Okay. So now I'll talk about the model. So I'll just give you a brief intuition about how the model works. It's actually quite simple. It uses a lot of kind of what looks like complicated Bayesian statistics, but underlying the model is actually very, very straightforward. So it's got the same generative process that I was describing before. That we start with a non-terminal, we rewrite it with an elementary tree, we rewrite all the non-terminals in the frontier with more elementary trees, and we continue until we have no more non-terminals remaining at the frontier. So at every stage, we have to describe the distribution over what we're going to do next, the ways we're going to rewrite. So imagine we have an S node here. We might have seen it a few times before. We might have seen it with as a small fragment, a CFG fragment, rewriting as NPVP. We've seen that 5 times, say. We might have seen it as a slightly larger fragment with George here, and we might have seen it as this larger fragment again with the count 3. So the idea here is that we try and repeat what we've done before in a similar, with similar proportion. So we'll do this with ratio 5, we'll do this with ratio 1, ratio 3, and we'll do something new with ratio alpha. So the idea is we then normalize this, which gives us our formula down here. But the idea is that if we've rewritten S a lot of times before, we're going to repeat what we did before, and we're going to do it in a similar way. So if this one was really predominant and we've seen it a lot of times, we're going to do that again. And if we do elect to do something new, then we're going to draw this from a distribution over trees. And this is going to be a very simple distribution, which I'll describe in a moment, which will give us a new tree. And bear in mind that the new tree can equal one of the old trees. So the probability ends up with this additional term here. You draw a new tree E with probability proportional to its weight, its count, plus alpha times the probability of drawing it as a fresh tree. And then there's just a normalizing term on the bottom here. Okay, so it encodes a rich get switcher effect. If we've used a rule in the past, we're going to use it again in the future. So we get this kind of reinforcement going on. And this is kind of the hallmark of Dirichlet processes and Pitman processes and Chinese restaurant processes within Bayesian statistics. The idea that we're going to try and find a clustering and we're going to get it to be self-reinforcing such that we get this kind of rich get richer behavior, which is kind of, you also see this described as a sort of Zipf-in distribution over language, which you see quite a lot. Okay, so more formally, the distribution over elementary trees, we model it as follows. So the elementary tree E, which we're drawing to rewrite non-terminal symbol C, we're going to draw that from a distribution G here. Now G itself, we're going to say, is drawn from a Dirichlet process, which is sort of a probability distribution from Bayesian statistics, which I won't go into sort of in-depth detail, but I'll give you an intuition about. We parameterize that in two ways, and that's a prior over the types of distributions we expect to see in our model. We have two parameters. We have alpha and P0. So alpha is the concentration parameter, which tells us how sparse we expect our parameters G to be. If we set alpha to a really small value, then we expect G to have most of the probability mass on very, very few things. If we set it to a very large value, we expect it to be a lot more uniform. And P0 is a distribution over trees, and I'll come back to what that is in a sec. But you can just think about this as a distribution over an infinite set of trees, and in fact biases towards smaller trees. Now, the cute thing about Dirichlet processes is that when you go to integrate out your parameters G here, which you can do in this framework, and you can do it analytically, and it gives you an incredibly simple function at the end. And what we end up with is saying that the probability of drawing tree number I, given all the trees that we've seen before, E less than I, so 1 dot 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 I minus 1, is just proportional to its count in the previous data plus this smoothing term. And the second thing that's very nice about it is that it's exchangeable. So if we've seen I items, 1 through I, if we see them again, or if we saw them afresh with a different permutation, so maybe we saw the ith one first, and then we saw the first one, then we saw the second one, and so forth, we end up with the exact same probability, which means that we can reorder our data and talk about seeing any item as the last one, and it ends up being logically or mathematically identical. And that allows us to do inference in this system very, very cheaply and simply. So, okay, I'll talk about the base distribution now, and I'll get into inference in a moment. So we need a distribution over infinitely deep trees, and what we frame this as a very simple generative process. And the idea is that we start with a symbol, which we have to rewrite, and we recursively expand it. And at each point, after an expansion, we can decide to stop or continue. So in the first step here, we decide to expand a noun phrase, perhaps it's a noun phrase and a prepositional phrase. Then we decide to stop, and we decide to continue. Then we expand the PP as a preposition and a noun phrase. We rewrite or we decide to continue. We rewrite it as a terminal string, and then we decide to stop here. And that's defined a tree. And that's very simple to sort of set up as a very simple generative process and describe the probability. So the expansion probabilities that we see here in step 1, 4, and 6 are just taken from a probabilistic context-free grammar, a maximum likelihood estimate over our training set. So the simplest possible model that you could think of. The continue versus stop options, so at each time we had to decide whether or not to stop. We call these beta, and we have a separate beta for each different symbol. So we learn whether or not we're going to stop for a noun phrase, whether or not we're going to stop for a prepositional phrase, all separately. And we draw these from a uniform beta prior, and I'll talk about how we get the values for these in a moment. But suffice to say that the net effect of this model is to bias towards small tree fragments, because larger tree fragments are going to be you're going to have to make more and more decisions. There are going to be more probabilities, which are generally less than 1, so you're going to get probabilities that diminish as the tree gets larger. So this is sort of there are dozens of different ways that you could describe Bayes distribution for this kind of model. We've chosen what we think is the simplest one, and it seems to work, so we haven't really gone to great lengths to make it more complicated than we need to. Okay, so now how do we train this model? How do we do inference in it? So recall that we have a training corpus, the tree bank, and the idea is that we can actually do this very simply using a Gibbs sampler. So the way we set this up is that, say this is our tree in our training set. What we do is for every node in the tree, we add a little number, which is either 0 or 1. And if, for instance, we want to encode that this noun phrase and this noun phrase are both substitution sites, then we put a 1 on the node. For the other nodes that aren't substitution sites, we put a 0. And we do this for every internal node but the root. So the root must be a substitution site by definition, so it doesn't need one of these variables. And then what we do is we try and sample values of these 0s and 1s, these substitution variables, to find a representation of the training set that is considered highly probable under our model. And the way we do this is using a Gibbs sampler. And so we do this in a few ways. So originally we proposed to do it using single variables. So we're updating one variable at a time given everything else. More recently we developed a way where we can do it for an entire sentence in a block. So we can update all of these in one step, which allows the inference to go a little bit faster. But I'll present the easier one because it's a little bit more simple to describe. So in general, the idea with the Gibbs sampler is that we have all these different variables. We want to be able to draw samples of all the variables values that are consistent with our model. So we want to draw them from the posterior of our model. So this is a sort of toy situation where we've got A through G variables, and we want to get the values of all of them. The edges between them show the independences, or they show the conditional independences in that if there's no link between two nodes, the two nodes would be independent, given the nodes that separate them. And in our case, all of the variables are going to be highly interdependent because they all depend on the counts of each other. So if you change one tree, you're going to have to that's going to affect the probabilities for all other trees. But the idea with the Gibbs sampler is that we condition on the values of every other node. So we have in our tree-based instance, we know all the substitution values for every tree, except in one case, in one node, we're going to resample a value 0 or 1. Then we're going to set that value, and we're going to move on to another random node in our training set. We're going to condition on everything else, and we're going to resample that one. So we're doing very, very local changes to every individual thing in the tree, and we do this over and over and over again until we start sampling from the distribution under our model. So just to give you a more concrete illustration, in our George H. Broccoli instance, we have this verb phrase node. We're going to look at resampling its value given everything else. So it was previously 0, but we're going to see whether or not it should be 0 or 1. If it was set to 0, then we end up with this tree fragment. So notice that this noun phrase and this noun phrase are all set as substitution sites. This one's set as not being a substitution site. So if we let that verb phrase not be a substitution site, we get this big fragment that ends up going down all the way here. If we set it to a substitution site, then it ends up cutting this rule in two. So we get SNP VP and a rule headed by VP. And we can score each of these under our model quite easily. Sorry, I haven't put the math in. We can quite simply get the probability of this fragment and the probability of these two fragments jointly. And then we can sample a new update. So we sample whether or not this VP is 0 or 1. Perhaps we choose it to be 1, and then we move on to all of the others. And we do this over and over again at every site in our training set. Yeah?
Before, say, the version 1, the version 0, you would run the base model for that?
So you get the base distribution probability, which is going to be relatively low, and then you add on the count, and then, yeah. So you get the count plus alpha times the base probability. In this case, you get alpha times, so the count of this fragment plus its P0 value, and similarly here, and then you compare the two, and you sample the value accordingly. So if this one's 70 or 3 times more probable than these pair together, then you're going to sample this value 3 times, and that value 1 if you were to do it over and over again. Perhaps I shouldn't have removed the maths. Okay, so what about the values alpha and beta? So alpha, recall, controls how sparse or how dense the parameters are, and beta controls when you stop, when you're doing this P0 expansion of creating your trees. So what we do is we sample these all at the same time. We're trying to be as clean as possible. We're trying to integrate out everything that we don't need. So we choose fairly vague hyperpariors. So the idea is that we're not going to express too strong a preference about the values of these entries, except to say, well, we have a gamma distribution over alpha, which allows it to take a fairly wide range of values, and we have a beta distribution over beta, which allows it to go from 0 to 1. And we can sample these updates during our training. So we do a Gibbs sample over our training set, and then we can sample new alphas and new betas, and we can update them quite simply. And as we do this over and over again, we end up, these just become other parameters in our model that get integrated out. And at the end, in fact, we have no free parameters left. We've managed to get rid of all of them, which is nice. You could argue that the hyperpariors are kind of parameters, but we set them to be fairly vague, so we've kind of got rid of them also. Which is very good. It's very rare to see an NLP model that doesn't really have any free parameters left. Okay, so now that we've managed to train our model by doing this Gibbs sampling and so forth, we need to parse. So given a test sentence, how are we going to find the maximum probability tree? So this is a bit more difficult in this model because of its infinite nature and because of the way it relies on this rich get richer effect. As you're creating a tree, you're actually changing the probabilities in your grammar. This sort of complicates everything. But in general, there's a quite easy way of doing it. You can reduce one of these infinite models, Bayesian models, into an approximating maximum likelihood model. Then you can sample from the maximum likelihood models. We use this using inside charts and chart parsing. We can get a whole lot of samples from the approximating model, and then we can sort of correct it into our model. And the idea is that this approximating model isn't quite going to be right, because it's not going to be encoding the rich get richer dynamic. But we can correct for that quite easily. And therefore we can collect statistics on the kind of trees that we expect to see from our model. So we get a whole lot of counts. In fact, we do for every test sentence, we do this 1,000 times. We get 1,000 trees. We collect statistics over those trees, and we use those statistics in order to come up with the best tree. And we do this in a few different ways. One is just saying what is the most frequent thing that we saw. So we sample derivations. We count the derivations. Whichever one we saw most frequently is the one we're going to return. Maximum probability parse. So if we throw away all of the tree substitution grammar information, all the substitution site versus not, and just record what the tree looked like underlying, when we're collecting our statistics, we can then pull off the most frequent thing, which will be the most frequent tree. And this is what people have done in the DOP literature, and they claim that this is very powerful, and we show that it's not actually that powerful, so it's kind of an interesting counterclaim. The problem is that in both of these cases, the statistics are going to be very sparse. The probability for a 80-word sentence of getting the same tree twice from this sampling arrangement is going to be exceedingly low, just because there's so much space of possible trees. And so what we do is we actually, or the best approach is to use this maximum expected rules method. So the idea is that we actually look at, when we're compiling our statistics, we actually look at the CFG productions that were used in the tree. So if its top level rule was to rewrite S as NP-VP, we record that as a statistic. And we do that for all the different spans of the string. And then we glue them together to find a tree that combines all the really popular CFG productions together. This is a variant on Goodman's approach for parsing. Okay, so I'll show you some experiments for the parsing model. Let's see how we go. So we train on the Penn tree bank. We do this in two different ways. Once we do it on a very small training set, and the second time we do it on a larger training set. So the small training set has 2,000 trees. It's a single section. The full set is a standard one, 2 to 21. And what we've done is we've set up our data in the same way that the Berkeley guys have done for their state splitting model. We do right binarization of trees. We deal with tokens that are singletons by replacing them with a special unknown token. It also encodes some information about their case and a few other small numbers of things. And that we use that to deal with unknown words at test time. We sample our model for 10,000 to 20,000 iterations, and we measure standard F1. This is like a standard evaluation metric in parsing, statistical parsing. Then we average the results over 3 runs. Now we have 2 baselines, a maximum likelihood CFG, and also the Berkeley parser, which is a state-of-the-art unlexicalized parser. It does very well. So now, just to show you on our small data set, this is kind of what happens as we're sampling. As we're sampling iterations across here, we can measure what the model thinks of the quality of our solution that we've got to thus far. So you can see here that it's kind of increasing in a kind of logarithmic curve, and that as we sample, it seems to be kind of plateauing out. Now I won't go into details of this too much, but these bottom set of curves are local samplers that update one variable at a time. And these top ones actually update an entire tree at a time. And you can see that it kind of converges a bit faster there. There are also different initializations shown here. Okay, now as for results, if we look at the F1 score, we have our baseline here, PCFG, which is a bit of a straw man baseline, admittedly, it's not very good. It gets around 60, but instead, using our model, we can get to around 75 or so. In fact, I think this one's up to 77, if I remember rightly. We've got 3 different methods for parsing. We've got the most probable derivation, the most probable parse, and the maximum expected CFG rules. And we can see that the most probable parse doesn't make that much difference against the most probable derivation. In fact, it usually beats it, but only very slightly. The maximum expected parse actually does really well. It gets another 3 or so F points, which is quite significant. Now, compared to the Berkeley parser on this data, now we ran it with the exact same data setup, which is not to its strength. We actually gave it our data setup, which isn't quite as good as their data preprocessing, which made it look sort of slightly worse than it would have otherwise. But in this case, it can also run Viterbi parsing, maximum probability derivation, and it also has an implementation of this maximum expected tree. And in both cases, it underperformed our model on this data. Now, sadly, that doesn't also carry over to the full data set, and this is sort of case for future work. But in this case, what we see is our model outperforms a PCFG by quite a lot. If we run the Berkeley in restricted mode, so it looks like our model, the same data kind of representation, it does 2 or 3 F points better, so there's definitely room for improvement there. I think it's largely a question of the inference method. If you run Berkeley with its best setting, you get 91.2, so there's quite a big gain there. The closest comparable DOP result is 83.8, so we've beaten that. It was a slightly different testing scenario, so it's not a strictly fair comparison there. But I think it's a fairly indicative value of where you get with just the standard DOP techniques. Okay, so now, what kind of rules do you get out of this model? And this is kind of the interesting thing, because you can interpret the grammars quite easily. You can look at the counts of what you've seen on the training set and look at the most common ones. So for noun phrases, for instance, we're looking at the top 15 rules for expanding them. And we see things like, there's the example here, quite common. This is our binarization. So whenever we see a noun phrase with 3 children, we binarize it to the right and add this NP with a bar on the top. And it's learnt to undo that, because that was a bad idea. It ruins the statistics, which is quite good to see that it's like that. We also see some more interesting ones. So we see things like noun phrase with a prepositional phrase, which is headed by of, with another noun phrase. So that's obviously very common. Here's another example of the same kind of thing. If we look at, for instance, lexicalized verbs, because this is sort of where it gets a lot of interesting things, we see it's like things like said it VP, rose some number of %, and then a verb phrase bar, which is going to be for something like yesterday or something, which is, this kind of thing is pretty common in the Wall Street Journal. Then we also have that closed equivalent, closed at, noun phrase, and then we have yesterday or last night or something. We also have things like agreed to and so forth. So we see a lot of kind of verb frames that it's captured, which is quite nice. Okay. Now, if we look at the hyperparameter values, this is another thing of interest. So recall that we had this these alpha values and the beta values. So the alpha values were the sparsity. If we have a very small value, we end up with a very sparse distribution. If we have a large value, we end up with a broader distribution. I think I might have this in reverse, though. So we end up seeing that the verbs, adjectives, and nouns tend to have a fairly broad distribution over rewrites, whereas things like coordinating conjunctions, EX, all these things tend to have one or two different strings they can rewrite as, so they can have a very sparse distribution. And it's like that verb phrases, prepositional phrases, and so forth get a value somewhere in the middle. So they have some degree of sparsity, but not too much. Now, when we look at their generalization score, we see sort of a similar effect, that some things should be generalized all the time. In fact, some things that have really consistent, simple rewrites, they can either be rewritten all the time or none of the time. It doesn't really matter to the model. And then the things in the middle can form the start of the rule or the frontier of the rule with sort of roughly equal probability. But I think there's sort of some interesting linguistic information potentially looking at these values that the model has inferred, which we're yet to sort of look at in detail. Okay, so just to summarize this part, so I've shown you a non-parametric Bayesian model of TSG. It uses a prior to solve problems with the maximum likelihood model and various other problems that you see with other DOP estimators. And it's shown that the performance can be kind of on par with other sort of very good models. It's not kind of state-of-the-art, but it has the potential to get there. Okay, so now I'll move on to the second part. Does anyone have any questions now, or you can cache them for the end, or whatever you like? Okay, well, I might as well plow on. So now I'm going to talk about machine translation. So we've talked about monolingual application, and now we're going to talk about a bilingual application. So recent work in maybe the last 5 or 6 years, there's been a lot of work, especially from ISI, looking at taking syntax on one language and trying to use that to bias the translation models to come up with much better looking outputs. And this has been quite good, especially on Chinese English translation. So it's a promising avenue, and we've started looking at how we can apply these kind of non-parametric models to this kind of application. So just to look at the machine translation pipeline as it exists. So imagine we're doing English to Chinese. We start with a parallel corpus like this. We have strings in English and Chinese. These sentences are known to be translations of one another. We automatically align the words. So we come up with these arrows saying that certain words align to other words from our expectation maximization trained models. They're kind of directional, and that's not so nice. They're not very consistent with each other, so we merge them together and we munge them until they look like what we'd like to see. Once we have this, we then extract some kind of grammar from them. It could be a finite state machine, it could be a grammar transducer, or various other things. And what we do is basically we extract n-grams from this data, and they're consistent n-grams on the other side after projecting through the alignments. And these form the rules in our approach. So here are just a few of the rules shown in color here. Then we estimate weights for each of these rules. So each of these will have a number, and then we can use these to translate. Okay, but there are certain problems with this. We cascade a lot of models here. We have a lot of heuristics. and they don't really play that well together. So for instance, word alignment often makes some horrendous mistakes. It doesn't incorporate phrasal information or syntactic cues. It could use that in order to generate some slightly better looking alignments. And in particular, things like long-distance reorderings that you often see, especially for German, English, and other language pairs. And if your alignment doesn't have that in it, then you're not going to learn a model that can do these long-distance reorderings, so kind of your model is kind of going to get nowhere with this kind of phenomena. And I think there are quite a few phenomena that the word alignment models just are completely incapable of finding. Idioms are another one, for instance. And so machine translation models are just absolutely pathetic at modeling this kind of data. And then, again, the second step is that there's ambiguity. Given your word-aligned data, how do you extract a grammar from it? How do you extract a finite state transducer? And there's no clear, obvious way, and the methods that have been used to date are often a little bit haphazard. So we present an alternative model that does joint synchronous grammar estimation, performing alignment and grammar extraction all at the same time. And the way that's done is by generating a grammar over string and tree pairs. So this is a form of tree-substitution grammar, but a synchronous one. So every rule does not just create some tree fragment, it also creates some string unit in the other language. And this is all integrated into a single Bayesian model. Okay, so it's highly based on this existing approach from ISI in the paper of Galli et al. 2004. It's in NACL. The idea was that we have a training instance like this. We have some Chinese, we have some English. Every corner of Singapore is filled with fun in this example. We have a tree, a phrase structure tree for the English side. We do word alignment in the standard way. We do the symmetrization. We end up with something like this. And then what we do is we apply their method to figure out the different fragments and the different rules that we can extract from this. So it's a kind of bottom-up heuristic for finding minimal fragments that are consistently translated. And I've shown that in color. So for instance, every corner and this substring here are considered a translation unit. And that is a subunit of this larger one in tan and so forth. Now, from that, we can extract the rules that we used. We've taken them apart here. And notice here that some of them are purely lexical. Some of them have, large numbers of units. Some of them have sort of these hash values, which indicate variables, which are connected to or aligned to another node in the tree. So that means that when you rewrite this noun phrase, it'll get glued in here before this token. This one encodes a reordering. Okay. Then we estimate weights on them using a fairly standard method. Okay, so one of the problems with this kind of technique is that, imagine you have a bad alignment. So this word corner is aligned to this word, which is Chinese for fun, I think. And that's going to kind of completely destroy this heuristic. It's going to get this massive rule in brown, which kind of spans the entire sentence. It has 1, 2, 3, 4 different variables in it, and you're probably never going to be able to use it on real data. So it's basically stopped you getting good translations for one unit, and it's meant that you've lost a lot of extra information in the sentence as well. So in general, you want your alignment model not to do this kind of trick. And one way of doing it is our approach, where we take a training instance like this, and we learn directly the rules. We do this all in one model. We induce the rules and their alignment all together, and that specifies our grammar. So if there are some really horrible-looking alignments going on, we're going to get some horrible-looking rules, and we're going to be able to refine that and change that until we end up getting nice rules, and that'll fix the alignment. So the two processes kind of can talk together and find something mutually compatible. Now I'll go into details on that just now when I talk about the model. Okay, so more formally, it's sort of set up in a similar way. So in this case, instead of just generating an elementary tree, we're generating an elementary tree and a string of words and the hash symbols, which are encoding our ordering. We draw these pairs from a distribution which is conditioned on the non-terminal that's being rewritten to G. And as before, we draw G from a Dirichlet process with an alpha variable which is controlling the sparsity or density, and we also have a base distribution. which of course is a little bit different to before, and I'll get into that in a sec. So, derivation here is a sequence of rules. Now, so the Dirichlet process prior, as before, we can state again that we want a very sparse distribution, which is very reasonable in this framework. We don't want a massive grammar. And in fact, if you run most of the MT models, you do end up with absolutely massive finite state transducers or synchronous context-free grammars of the scale that you can't actually even represent them on disk. So this is kind of very important. I'll just go through what the generative process looks like for creating a pair of a tree and a string. So we start off with the S symbol, and we decide to rewrite it as three things, a noun phrase, a verb phrase, and a full stop. Then we decide to rewrite this noun phrase with an expansion, noun phrase, and preposition phrase. And we decide to this rule has a reordering of the variables, so we insert this in here, and we have the alignment. Then we go through the next frontier node, the NP, and we rewrite that. We also rewrite the thing, the hash it had in the string representation, and we end up with every corner, and so on. We keep visiting the frontier nodes, applying rules from our grammar. So here's the one for of, and so forth until we have a form representation. So that's our generative process in 20 seconds. Now the base distribution here, which I haven't specified, so the distribution is now an infinite distribution over the space of tree fragments and string pairs. We still want to penalize larger rules compared to small rules. So we measure that, we do this again using a recursive formulation, which penalizes rules based on the number of rewrites they have. And the way we do this is we decompose our P0 over the elementary tree and the word strings into two distributions, probability of the elementary trees and the probability of the word string. And we assume that they're independent. So the probability of the elementary tree given the symbol is exactly what we had before. That's the thing from the monolingual parsing part. And the probability of the word string given an elementary tree is just a really a naive and simple distribution. We decide to generate 0 or more terminal tokens, and we draw these all randomly, uniformly. Then we insert for every non-terminal frontier node in E, so the number of variables we need, we insert each of them randomly at some point into the string in order. So this could be made a lot more elegant and a lot richer, but this seemed to suffice. The net effect is a bias towards small grammar rules with small rules, because the number of operations you're going to need in your probabilistic formulation is going to get bigger and bigger and bigger as you get larger rules. Okay, so we train it using a Gibbs Sampler as before. We have a slightly more complex representational problem because we're not just interested in how we split the tree up into parts, how we segment it, we're also interested in what it aligns to. So every node we decorate with an alignment variable as before, but the alignment variable has to say, is the node internal to a rule, or is it the head or footer of a rule, and also specify the span of tokens in the string. So together, if we know the span and whether or not it's the head of a footer or a rule, then that'll specify the complete derivation within the synchronous tree substitution grammar. So we then define a Gibbs Sampler to update each alignment variable, or it also applies to pairs. There's a special operation to make it move a bit faster. Now, bear in mind that when you update one variable, it can invalidate others because you can't have overlapping spans, and there are a whole lot of constraints on what alignments can actually be consistent with the tree string pair, which I'll show you in a sec. So doing these updates is actually quite tricky. You have to be quite careful. So here's an example of the sentence from before, annotated as such with the alignment variables. So we have some alignment variables that are the empty set. They're not aligned to anything. That means they're internal to a rule. We have other ones that are given a span. So we'll just highlight a bit of this. So this NP is from span from word 2 to word 6. So the span 2 to 6 here. The DT here is from 2 to 3, and the corner here is, the word for corner is from 3 to 6. So this specifies, that representation specifies this set of rules. shown here in color. So you can see here that the span of the children have to be strict subsets of the span of the parents. They can't overlap with their siblings, and these are the kind of constraints that we have to make sure that we preserve. So the way we do our updates is we look at each of these variables and we try and change their values, and we sample them stochastically. So, for instance, if we're looking back at our every corner fragment, we're looking at the alignment variable for corner. It could have a whole lot of values. It could be aligned to nothing. It could be aligned to various different strings which are in the range 2 to 6 spans, as long as they don't overlap this 2 to 3. So they could be anything from 3 to 6 or a subset. So I've shown some examples here. We have the one where it's not aligned to anything, in which case we get this big fragment for the noun phrase, lexicalized with corner, and also lexicalized on the Chinese side. If it's aligned to 4 to 5, we end up with just this token here, ge, aligned to corner, and we can align it to the entire remaining bit. So we can see how these are all the different options. We then get a probability for each using the Dirichlet process formula. Simple count plus the base distribution smoothed by alpha. And then we can sample a new value. Okay, so that allows us to make some local changes. We also had another one which allows us to make some extra changes. So we look at pairs of nodes that share the same parent. So for instance, every and corner share the same parent. So what we can do is we can swap them around. So we swap the span 2, 3 with 3, 6, and we end up encoding a different rule. So every and corner being monotone translations versus every aligning here and corner aligning there, and the noun phrase describing a reordering operation. So we can sample for each of these instances whether or not we should flip. And so we've pre-processed our trees to be binary branching, so this operator can apply at quite a few places in the tree. Okay, so together those those Gibbs sampling operators can allow us to move from one state to another state and allow us to get to hopefully get to a state where the model is quite happy and finds that the segmentation and alignment of our data is a highly probable one. Okay, so the way we've run some experiments on this, we've evaluated for Chinese English. We train on a part of the NIST data set, around 300,000 sentence pairs. This is a fairly sort of well-established, good set for Chinese English, and it's a reasonable size. We use fairly standard test sets. So we have a development set from MT02, the NIST evaluation in 2002, and then we have a test set for MT03. We impose some length constraints on it to make it tractable, because parsing with these models is actually really, really tricky. We segmented the Chinese and we parsed the English. I think it was with the Stanford parser. So we had a baseline implementation, which was our implementation of the Galli et al. Heuristic, using Giza++ for doing our alignment. And our model, we sampled it for 300 iterations. We used the last sample for defining our decoder, and then we ran our in-house decoder to get the best strings for all of our test translations. We initialized our system with the baseline system, so that it was somewhere near the solution, so that it didn't have to train for too long to get to a good solution. And we set the hyperparameters by hand rather than fitting them to the data. Perhaps we could have actually learned them at the same time, but we didn't choose to in this model. So one interesting thing is if we look at the statistics over the grammar, which is the model induces. So if we look at the learned grammar and the number of rules versus the height of the tree fragments within it, so we're just ignoring the Chinese side and just looking at the English side of the fragments, and we notice here that the baseline system, the GHKM, has fewer small fragments and more larger fragments. Our model ends up with a grammar of roughly similar size, but with many more small fragments and many fewer large fragments. So this is a good thing, because we think smaller fragments are actually more reusable and more likely to help us at test time. We can also look at the number of terminals, I think in the Chinese side here, and we see that our model has learned more unlexicalized rules than the previous model, and still has a similar decaying distribution over slightly lexicalized rules. In fact, it doesn't have very many sort of massively lexicalized rules, which anything with, say, more than 5 tokens in it is probably a result of an alignment error. So it's actually managed to fix a good majority of these, which is great. Okay, we can look more specifically at the rules. So if we look at rules that expand the noun phrase and have this Chinese token de in it, so de token is used as the possessive particle, like apostrophe s is used in English. Often it's the noun phrase is written in the reverse order to English, so that's why it's kind of of interest to us, because it encodes a common reordering that we often see. So in the baseline grammar, we get some very simple rules, encoding monotone translation, monotone, and we get a reordering here for a noun phrase and a prepositional phrase. When we look at what our model learns, it learns slightly deeper rules. So for instance, the second one here, we have a noun phrase with the, noun, of, noun, and it's learnt the reordering. So this is really the rule that you'd like it to learn. And it has, not as the most popular one is to learn that noun phrases start with the, which is fine, but it has learnt, and even the fourth most popular one also does something very interesting with the reordering. So it's good to see that it's been able to do this. Okay, so the translation model, it was an in-house CYK decoder. We used a very simple feature set based on previous work by Marku. We didn't do a great lot of work to tune it to get it to work really well on this data. We just spent a few months trying to get it working instead of ISI's a few years. And what we ended up managing to achieve was an increase over the previous baseline, which is a very strong method, so it's great to be able to outperform it, even if it's only slightly. And we intend to try and sort of reduce this limit so we can run it on larger data, and also try extending the model in different ways and new inference to maybe get an even higher result. Okay, so now I'll just summarize. So presented a generative model of tree-to-string grammar induction. It induces a weighted STSG and also an alignment all at the same time. And this can be seen to address the disconnect between word alignment and the induction of grammar models that's done in translation. And what we see is it gets a more parsimonious grammar than the previous heuristic approach, and it gets a small improvement in translation performance, so it's quite promising in that regard. So in general, there's a bit of future work here. So improving the prior, the back-off distribution, to have things like hierarchical prior, such that we can talk about the rule shape, so we could start generalizing between, say, different verbs that are all lexicalized, or other different patterns that we see repeatedly over and over again in the data, such that we can get more reinforcement and more probability on these common fragments. I think a very important thing is getting a better inference technique. So we've done this in a very simple way using Gibbs samplers. Other techniques like variational inference could be a lot more promising for getting better mixing and more accurate decoding. We want to adapt the approach to dependency trees. We think that's quite an important thing to do rather than just using phrase structure trees. And we also want to induce other types of grammars as well, like finite state transducers, synchronous context-free grammars, which Phil is going to talk about, tree adjoining grammars, combinatorial grammars, and so forth, because we think this is quite a flexible framework that you can glue in sort of a whole lot of different grammars. And we also want to do fully unsupervised grammar induction, that is dropping the trees as well, which I think Phil will talk to you. If you have any questions now, please feel free to ask me, or we can move on with Phil's talk.
Maybe even in the first half of the talk. There's the alpha and how many of the
okay, so there are roughly 50 or so categories, maybe 70 or so categories. So that's the number of part-of-speech tags plus the number of phrasal categories in the Penn tree bank. I can't remember off the top of my head. It's less than 100. That's the number of alphas. There are also a beta for each of those. So it's 150 or so. But we tried tying them together. It didn't really make that much of a difference. I think we got a slight improvement in performance by letting them be learnt all individually. Any other questions? Andrew?
I have a question about the trees. You doubted the alignments, and the method is implemented in order to handle misaligned or ignore the GISA, the automatic alignments overall. And the thing Phil is going to present will probably completely get rid of the trees. Would there be something in between that you would approve, you would include some of the supervised edges from the trees, but you would be able at a certain cost to ignore some, like if humans or the parsers made the trees badly. So like
you could include it as a prior over your trees potentially. Yes, that's an interesting idea. So at one level, including the trees actually makes inference a lot more tractable. So it's kind of attractive in that regard. And the stuff that Phil's going to talk about has more tractability concerns because it's a much broader space to search. If you were to include, say, a parse forest from a parser as your representation of the trees, then you're going to have to embrace a pretty nasty complexity term. But theoretically, and maybe it potentially is practical. It's an interesting idea. Or you could include it in a prior, that's another thing, within a sort of fully unsupervised model. Okay. Lovely.
Move through it quite quickly to not keep you too long. So I'm going to follow on what Trevor's been talking about by addressing this question, well, what if we didn't have a parser? If we didn't have a tree bank for the languages we were talking about, can we still do some sort of unsupervised learning of trees for our translation models? And of course, if you think about the sorts of translation problems we might be interested in, there are a lot of languages out there where we don't have tree banks. So I think it is a very interesting question about whether we can induce some of this structure useful for translation, not necessarily matching what a linguist would like us to induce, but useful for translation to learn things like reordering. So a couple of quick motivating slides. We've already had quite a lot of motivation, but just coming to this question of what can we currently do with translation models? In this case, we'll look at, well, what if we have a phrase-based translation model? We've trained it on a lot of Arabic data. This is just the Moses translation model. And this is the current state of the art. If you read that translation, it's really good. So for Arabic, we can actually produce some really quite surprisingly good translations. If we try a different language, like Chinese, same sort of model, same amounts of data, the result is entirely different. If we try and translate Chinese into English, we almost always get terrible results. And I'm sure you're all probably familiar with this with Czech as well. There's some languages which are just a lot more difficult than others to translate between. And there's some languages that just don't suit the current models we use. So the current models we use, like Moses, phrase-based models, are very good in certain circumstances, but other times they just fail entirely. So we'd like to explore some different ideas. And in this talk, I'll talk about trying to induce synchronous context-free grammars from parallel corpora without any annotations. And if any of you are familiar with Dekai Wu's work with ITGs, this is very similar. And in some ways, what I'm trying to do here is make the work he described quite a while ago now, maybe almost 15 years ago now, make it actually tractable on real translation tasks. So current approaches to inducing grammars or phrase tables, one, they're based on heuristics. We first use something like GISA to align data. We then use a different heuristic to extract translation rules from that. If you're familiar with David Chang's Hiero, we have certain ways of extracting synchronous grammar rules from aligned corpora. And these models don't match each other. So although your synchronous grammar might be able to represent or able to do a long-distance reordering, your GISA alignment model can't. So if you're learning your synchronous grammar from an alignment model which can't actually model a phenomena you're never going to be able to model it in your synchronous grammar. So you need some match between the approaches. So I'll describe how we can, instead of using something like geezers to align our data, how we can use a sort of phrase-based, grammar-based alignment. And what I'll describe, the experiments go partway to achieving our aim. We still have some reliance on some of the current techniques like Moses and such. So as a sort of end goal, you could imagine if we just had a parallel corpus, what we'd really like to be able to do is induce something like this, where I've got labels here. So we're inducing a tree, an alignment between two sentences, and these labels just are some labels we've induced, and maybe one corresponds to an S label, maybe 4 corresponds to a noun phrase, and we can just learn these from data. That's very ambitious, so let's just worry about learning the structure of the tree first, and that's what I'll talk about in this talk. Can we learn this structure just from the text? And then we're going to include worrying about learning phrasal alignments. So we're not just going to try and learn one-to-one alignments or one-to-many alignments like Giza, but we want to learn many-to-many alignments in this sort of tree structure. And just a word about the symbols I use here. The circles are used to denote emissions in the grammar, so the terminals. The squares are non-terminals, which are monotone, and the diamonds mean that some sort of reordering has gone on. So if you follow this tree through, you'll see that there's a reordering here between these two phrases, and here again there's a sub-reordering. So I'm just denoting that with these, and I'll refer to that as rule types. So if we're going to model these trees, we're going to have to come up with some sort of generative story about how our model produces the parallel corpus. So that's going to be a relatively simple story. We're going to start with a starting node. So this is the top of our parallel trees. And down here at the bottom, I'll describe the actual statistical distributions that I'm going to use to model these. If you're not familiar with this sort of notation, don't worry too much. Worry more about what's going on up here. But we say we're going to first draw a rule type from a multinomial distribution. So we're going to choose what sort of node this should be, and we've chosen a square. So that means it's going to be a monotone translation node. So we've chosen a monotone translation node. So now we know we have some children that we need to fill in. So we're going to choose the actual rule for this. Sorry, I'm one step ahead. So now we choose the type again for the child, and we choose a circle, which means that's going to be an emission. Then we choose what the actual emission will be, what the actual terminals will be. In this case, we've got a Chinese question mark translating as an English question mark. That's not a very exciting rule. Again, we go through this process. So we now draw a rule. This time it's a diamond, means there's going to be a reordering underneath that one. And so we just keep recursing, keep going through this process, drawing from multinomials for types and then the rules, and keep generating right down to the leaves and generating the sentence. And because of the reorderings, I put the terminals in the right position. So this is the way that the parallel corpus we're saying is generated. And this is a probabilistic model, so for each step we have a statistical distribution. So what we're saying is that we want to learn this. From observing the strings, we want to learn the parameters of these distributions. So to summarize this with an equation, it's very simple. The probability of a tree, which I call a derivation, so any given tree, we'll call it a derivation, it's simply the product of all the rules we used. So the probabilities of all the rules and the probabilities of their type. Because at each step we're choosing a type, then we're choosing a rule, then we're choosing a type, then we're choosing a rule. Very simple, the probability of a derivation is just the product of all these probabilities. So what we're going to do is we're going to call on our favourite statistician, the Reverend Bayes, a fellow Edinburgh alumni, and model this with Bayesian statistics, just like Trevor has been talking about previously. And this gives us a number of advantages, and this is what's actually going to allow us to do this tractably, which is sort of counterintuitive if you're familiar with a lot of the literature with Bayesian models. Generally, people associate them with making things less tractable. In this case, it'll actually make things more tractable. So again, we have a bit more of this Bayesian mathematics. Don't worry too much if you don't follow all these Dirichlet distributions and such. I'll just try and convey the intuition. So again, we're going to have two important distributions that we want to model. We want to model the productions which are internal in the tree. So that's our monotone productions and our reordering productions. And as I said earlier, these are distributed according to a multinomial stated up in the top corner here. And what we're going to do is we need a prior distribution. In the Bayesian statistics sense, we put a prior on the parameters of this multinomial. And the most popular way of doing this is using something called the Dirichlet distribution. That has some nice statistical properties that are useful. In particular, they're useful because we can integrate out the parameters of these distributions and just be left with this statement here. And this looks very similar to statements that Trevor was using in the previous models. And why this is useful, so these numbers here are counts. So this n is the count of the number of times we've used a particular rule. So the probability of a rule being used again is proportional to the number of times we've used it previously, with this alpha smoothing term. So if you think about why this is useful, and in particular useful for scaling, at any stage to work out whether we're going to use a rule, all we need to know is how many times we've used it previously. So we don't need parameters for every possible rule the model could produce, like they do with the ITG model, every possible phrasal translation. Obviously, there's huge numbers of those. And we don't want to store all those parameters. But in this case, all we need to store are the ones we've actually used. So if you think about that, that's going to be a lot less. In fact, it's going to be roughly linear in the size of our corpus. So this is going to be much more manageable. Now all we essentially have to store to do inference is our current set of trees for our corpus. So suddenly things become a lot more tractable. And that's why this approach is useful. The second distribution, which is a little bit more complicated, is this omissions distribution. So this is where we're actually producing translation phrases. And here we use a bit more sophisticated statistics. And we use this idea of hierarchical Bayesian models. And why this is useful is because it gives us something that's very much like backoff in a language model. If you think of a language model, a trigram language model, you back off from trigrams to bigrams when you haven't seen the trigram often enough. We want something very similar in phrasal translation models because phrases are going to be very sparse. So we want some sort of way of smoothing them, sharing probability between phrases which look similar. And we do that so what this equation here means is that we're going to back off, P1 means our back off distribution is going to be a product of the frequency of the source side times the target side. So what we're going to do is say, the top level we're going to look at how often we've seen these two phrases as a translation unit, and we're going to smooth that with how often we've seen the source and the target independently as translation units. So this becomes a hierarchical model. And this has now become something called a Dirichlet process. I won't labor the statistics too much, but this is something that people refer to as a Dirichlet process. And we have an extra distribution in here, a Poisson. And the reason that's in there is because we want to encourage the model to choose short phrases. So we have an extra prior saying we expect phrases to be short. Otherwise, the way the statistics in the model work, it'll choose bigger and bigger phrases, which we don't want. We want it to find the smallest phrases which describe the data well. And again, we end up with one of these equations which looks just like the previous one, where all we need to do is worry about counts in our data. So that's our model. Now again, we want to be able to learn this model from data. So we're going to use, again, a Gibbs Sampler, just like Trevor's been talking about in the previous talk. This is different to how people have tried to learn these models previously. They've used dynamic programming, and the problem with that is that we get this complexity, which we say is sort of in order n to the 6 in the length of our sentences, and that's far too high. And if you look at previous work with inducing these sorts of grammars, they're always talking about sentences of length 10 words. But no one's really been able to do it on proper full translation corpora, more than a few thousand sentences. But by moving away from the dynamic programming, we're going to use Gibbs sampling. We can actually do this on decent-sized corpora. So again, this Gibbs sampling comes down to having these local operators which change our current sample. In the work that Trevor talked about, there was a fixed tree, and you had to sample these segmentation of the tree and the alignment. Here we have an extra problem that we don't know what the tree is as well. So we have to be able to change the tree and the alignment at the same time. And we'll do that with two operators. The first operator splits and merges nodes in a tree. So if you imagine we have this node to start with, then we look at all possible ways of reconfiguring that node. So we could keep the current setup, which is a 2 to 3 phrasal translation. We could split it up in this way into two new nodes, or here I indicate a reordering with these, so we could reorder them, so we could have them monotone, and there's all sorts of different splits. These bars here mean null, so it's an empty. So we could choose that this side as an empty translation, and this side translates as a 3-word phrase. So for any node like this, we consider all these options, and we sample one. We call that the split operator. We have a second operator which adds and removes nodes internally in the tree. So imagine we have a configuration of a tree like this, then we sample collapsing these two up into their parent. And this is where I diverge slightly from previous work with ITGs. Here I'm actually allowing non-binary branching nodes, but that helps us with the sampling. So we can move back and forth between these configurations. Now if you think about what we can do with just with those two samplers, we can move between every possible tree configuration. So we can keep deleting nodes from a tree. If we want, we could flatten the tree into one huge phrase. Then we could resplit it up into different units, and we could move between all possible trees. So I'll give you a brief sort of demonstration of what this work looks like in action. So imagine we have this Chinese to English translation. This is our current sample that we're working with. I've highlighted in green bits that we're going to choose to apply our operators to. And so we're going to apply our split merge operator to this section of the tree. And we're going to sample that we should merge all those units into a single node with one phrasal translation. Then we're going to move on to a different part of the tree. And we essentially select these parts of the trees at random. And we're going to look at this node here and say, should we keep that node or should we get rid of it? And we're going to sample that maybe we're better off without that node. We're going to go back and look at these three nodes, and we might choose that we can add a new node again. And we're going to keep doing this thousands and thousands of times. And we again look at the terminals of this section of the tree, and we choose a different segmentation this time. So we move the determiner over onto the noun phrase. And by doing this thousands and thousands of times, we're going to walk through lots of different tree configurations and lots of different alignments, and eventually the sampler will settle down into the high probability space. Okay, so I'll quickly run through how we evaluated this model. So what we do is we first we need to start the model with a first derivation. So we take the output of an existing alignment model and then morph it into a binary branching tree. We then take about 1,000 samples, where a sample is a full pass through our corpus, and we call that a burn-in. We just throw those samples away, and that gets us that moves us away from our starting point and gets us into the good part of the distribution. And then for the next 500 samples, we collect samples and use those collection of samples to estimate a distribution over translation units. And finally, we use those translation units in an existing MT decoder. In this case, I'll just present results with the Moses decoder, but we used a number of different decoders. So the first experiment is on a small corpus, the IWSLT corpus, translating from Chinese to English. It's quite small, 40,000 sentences, but it does have the occasional long sentence in it. So the longest sentence is about 75 words. And you couldn't run a dynamic program on sentences that long. So it's good that we can run this model quite reasonable time. This is the normal performance you get from Moses. This is what you get if you estimate the translation units using this Bayesian approach. So it works quite nicely on the small data. We want to do it with a lot more data, but to do that we're going to have to distribute our sampler, because the way I describe the sampler, it's just a serial process on a single computer. So we'll distribute it. I'm going to gloss over the problems this causes because it takes a while to describe, but basically there's a paper by Newman at NIPS which explains how you can distribute these samplers. It is an approximation though, so we'll have a quick look at the approximation before presenting the results. But now we move on to these bigger corpora taken from NIST. This Chinese English one is the same one that Trevor talked about, 300,000 sentences. Again, we've got some long sentences in there to test whether we can really work with real length sentences. And I use a similar setup to previously. We also have an English-Arabic experiment in there. So firstly, a quick slide that just says, this compares our distributed version to our single process version, so a bit of detail. And what this slide says is basically our distributed version, which is the dotted line here, gives a very similar performance to our single one. So this is log likelihood of during our training. So this distributed approximation seems to work. It gives us something very close. So that's good because now we can, in this case we are only using eight CPUs, but we could conceivably use thousands if we were Google, for instance, and get good scaling. So what happens when we apply this to Chinese? The story's a little bit complicated, but I'll go through it. So in the black is Moses. The blue here is just like the previous evaluation. That's the model using our estimation technique. This grey bar is the initializer that we start our sampler from. So I actually said that how we initialize the model is to take an existing alignment and force it into being a binary branching tree, which of course means throwing away alignment points. So I evaluate that as well, because that gives us a baseline. We should do better than our initializer. We do in two cases, but in this case we actually do worse than the initializer. The initializer does better than Moses and our model, which is interesting. But generally for the Chinese data, this sort of approach helps generally. When we look at the Arabic data, it doesn't help. In fact, it's a negative most of the time. And this is a bit of a theme with Arabic-English translation. If you've followed the research, switching from phrase-based models to synchronous grammar-based models often hurts performance when working with Arabic. In this case, our model is often worse than the baseline. In particular, the initializer does extremely well. So this is a bit of an interesting phenomenon that we still have to understand. So if we look at some of the Chinese output and consider what's going on, why it might be giving better performance for Chinese. So this alignment on the left is what you get from Giza, the standard word alignment method. And you can see it's quite strange. You get alignments like this, which don't make a great deal of sense. This is the alignment produced by the Bayesian system, and here because of course we're producing a tree, I've shown the bracketing on the bottom and sides here. And this is a much nicer alignment, and it's essentially correct. And you can see that we are learning these little phrasal alignment units, which is quite good, and there's some quite interesting reordering going on there. So in some ways you can think of what's happening here is that we're cleaning up these alignments. So these are quite noisy, and we're getting something much cleaner. And part of that is because we're forcing it into a tree structure and learning in a tree structure. Okay, so I'll finish up there. Keep this quite short. So what I've described is basically this way of estimating these synchronous grammar models using Bayesian techniques, using a local Gibbs sampler. This allows us to do this sort of inference on lots of data, a lot more than people have previously been able to use. And sometimes it helps. It helps with things like Chinese, where there's actually difficult phrasal and long-distance reordering going on. Doesn't really help with something like Arabic. So, thank you. So yes, any questions? And I'm sure you can ask Trevor more questions about the first half as well. Well, we're not dealing with non-productivity at all, and it does make it more difficult because then you don't have a nice tree. So, there's this trade-off. If you want to work with non-productivity, you lose the word order. It's very difficult to maintain the word order and work with non-productivity. So it is a difficult problem. For the NIST ones, it was just a single computer with 8 cores. So an 8-core machine and using all 8 cores. The IWSLT ones were just a single. No, it probably took a day to run the full experiment. It's probably not too different to Giza, which takes quite a long time to, if you run it right through to Model 4, it takes quite a long time to run. Yeah, although you don't have to start with the end of Giza, you can start earlier. You just need some starting point. Yeah, so everything I presented here came from a paper presented at ACL last year. I have another paper at the bottom there that we'll present at NACL, where we looked at this. We looked at the inference in particular a lot more, and we looked at random sampling, random starting points. And the sampler I've described here doesn't work with random sampling point. And we have another sampler which is based on something called slice sampling, which does work with a random initialization. Unfortunately, it's slower. So there's a trade-off